Hello, everyone, and welcome to our third lecture in our course on general psychology. So this is week two, and we've already talked about the history of psychology. We did that last week. This week we're going to talk about the science of psychology. So we'll start off by talking about science in general, what makes a science, what classifies something as a science, what are the properties of a science. And then we'll talk about psychology in particular, and some of the challenges that working with people and people's minds, uh, what that entails and how we try to address that. So, for overview, uh, we're going to be looking at the science of psychology, and we'll talk some about the history of the scientific method. And as we'll see, the scientific method is an empirical approach. That is, it's a way of trying to understand the world around us using evidence and observation. People talk about the scientific method, but we're really going to talk about some of the properties of the scientific method, not just use the term and then leave it at that. What does the scientific method mean? What is that method? We'll talk about the data that result from the scientific method, from observation and measurement. And how do we categorize data? How do we describe it? What do the data tell us? And how do we describe patterns in the data? So if the data isn't just a bunch of random numbers, if there's a story to be told from the data, if there's something important in there, how do we relate that story to others? Also, how do we avoid telling the wrong story? So the data, if they're interpreted correctly and analyzed correctly, can tell us a lot, especially about a particular phenomenon if we've really designed our experiment well. But it's possible to take those data too far or to misinterpret the data, to say that the data say something they actually can't. Uh, and we'll talk about how we get around that problem. How do we identify pitfalls like that and avoid them? So what we're going to do in this session is talk about the empirical approach. Why is it good? What historically did it have to come up against? What were its competitors? And we've already talked some about that last week, but we'll get into the empirical approach a little more concretely. We'll talk about how to describe data visually and numerically. So even a simple experiment can generate an extraordinary amount of data. And how do we wrap our heads around it, so to speak? How do we say something meaningful from the data if there's something meaningful to be said? How do we notice it? How do we relate it to other people? Also, we'll say something about correlation. And correlation is when two events or two variables seem to be related to one another. That one psychological trait is related to another one or related to behavior in some way. And we'll say how we have to be careful not to necessarily think that one thing causes another. So you've probably heard the phrase correlation does not imply causation. So we'll unpack that. How do we avoid thinking that? And what scientifically can we do to avoid that issue? So a little history. So first, talking about science itself. And science is an empirical process. So that means that science acquires knowledge through observation. It means we actually need to experience things in the real world and experience them in sort of a principled fashion. We try not to bias our measurements. We need multiple measurements. There are a lot of ways to go about something empirically that will make your observations and your conclusions more likely to be true. And one of the things about an empirical discipline like science is that the evidence needs to sort of speak for itself. So if you collect observations, uh, the observations will indicate what the truth is, even if that observation or that conclusion isn't what people thought before. That's okay. Sometimes observations confirm what people think. Sometimes they disprove what people already thought. And so we often, as human beings, uh, get attached to old ideas, get attached to old ways of thinking. And just because they're old doesn't mean they're necessarily right or wrong. So again, we need to let the evidence, let the data indicate what the truth is, whether it goes against old notions or not. And here we've got a picture of Galileo, who was famous for observing the stars and planets, and he had a theory that the Earth revolved around the sun, and his observations fit with that idea. But that went up against previous ideas, primarily from religious texts, that the Earth was the center of the universe and that everything, including the sun, revolved around it. And so there was a tension there. So whose idea was right? Galileo's was based on empirical observation. He collected observations and evidence and made a conclusion based on those. And he was actually almost imprisoned. He ended up being put under house arrest by the church for heresy, for going against the church's teachings. And he got out of imprisonment by backing away from his observation. That's one of the dangers of not letting evidence speak, of holding on to older ideas when perhaps we shouldn't. That Galileo was basically bullied into stepping away from his ideas and retracting his claims. And he said, "Okay, I admit it. You know, my idea that the Earth revolves around the sun was wrong. That these things don't move the way that I said." But then later on, he hinted that his observations were actually right. So when it came down to going to prison, he backed away, but he still knew what his observations said. So then, of course, there's the scientific method. And what does that involve? So the scientific method, again, is an empirical approach, and it attempts to find the truth, something about the way the universe works. Here we're obviously interested in people, how people work. But either way, trying to figure that out via evidence. And that evidence is going to come from observation. And then once you have some evidence in hand, you can develop what we call a theory. And a theory is a kind of explanation that's consistent with the current evidence. It's an explanation of how the world, the universe, or people operate. And from a theory, you can generate a hypothesis. That is a prediction. So if my theory, for example, revolves around gravity, saying that bodies with mass tend to attract one another, then I can hypothesize that if I drop one mass, if I let go of it, that is, it will move toward the Earth because masses attract one another via gravity. So my theory is about the attraction between bodies with mass. My hypothesis is if I do X, Y will happen. And of course, that framework is what we call falsifiable. My hypothesis could be proven wrong. So if I let go of an object and it doesn't move toward the Earth, well, then I've just falsified my prediction. My prediction didn't come true. And so some ideas, and your book points them out, are not falsifiable. If your theory, if your explanation doesn't allow you to make a prediction that can be proven or disproven, the disproven part being important, then that's not a falsifiable hypothesis. So the word theory gets thrown around and sometimes gets abused a little bit. Some people colloquially will use the word theory to mean something that's not supported, something that's questionable, something that's perhaps flimsy. Whereas that's not the way scientists use the word theory. So theories do vary in the degree of support they have. That's certainly true. But just because we call something a theory doesn't mean that it's not true. It doesn't mean that we question the basis of the theory. It could be a perfectly good theory. So, for example, evolution is a theory, and a lot of people will disagree with evolution and say, well, it's only a theory. And they're using theory in this colloquial sense to mean something that we're only guessing at. And a theory is supported by evidence in science. And so evolution is a theory, but so is gravity. In fact, we understand way less about gravity than we do about evolution, for example. So theories vary in terms of how much support they have. But just because we call something a theory doesn't mean that it's flimsy or that no one believes it. A theory, again, is supported by good evidence. And theories can't be proven. So if you see in the news that they've proven a theory, all they've really done is given more support to it. You can never really prove a theory. You can disprove it. So if, for example, my two bodies mass experiment, if one moves away from, if one mass moves away from the other, then I've disproven something about my theory. Maybe it needs to be adjusted. Maybe I need to throw it out entirely. So you can disprove a theory. It only takes one observation that disproves your theory. You can keep on adding observations that support it, but you can never really prove it. Just like one of the famous examples is, for a while, people were only familiar with white swans. And you could put a theory forth that all swans are white. So no matter how many more white swans you observe, you lend support to that theory. But it only takes one black swan to disprove it. Okay, so we've said that the empirical approach uses observation as evidence, and hopefully lots of observation. So how do we observe things? And of course, the most obvious way is just to use our senses to see something or to hear something, and then record our observations. But there's some trouble with that, usually. And then that is that the senses are a fine start, but they're far from perfect for a number of reasons. First, your senses aren't necessarily sufficient. So if you're looking at something very far away, like stars, or very small, like microorganisms, the phenomena you're interested in aren't available to you as observations to the naked eye. Similarly, there are sounds you can't hear. There are chemicals you can't detect by smell or taste. And so some observations just aren't within the range of our senses. And so our senses won't suffice for those things. They can also be inaccurate. And over here I've put an optical illusion that hopefully will work in video form, we'll see. But what this illusion consists of, if you look at it and move your eyes, it's a grid, but you'll see dark spots appear on the grid as you move your eyes around. And the fact is those dark spots are illusions. They are artifacts of the way your visual system works. So your senses can be not just insufficient, but inaccurate. They can give you an impression of what something is there that isn't, or vice versa. So your senses aren't necessarily an accurate representation of the world. By the way, neither is your memory. So even if you sense something accurately, if you're depending on your memory later, that can often be inaccurate as well. Also, your senses are only the first step if you're using them. The data also have to be interpreted once you have the data. And the data can be really complicated, more than you can keep in mind, more than you can wrap your head around in a sitting or as you're observing. And this is what we call complexity. So when the data are, as the name suggests, complex, they can be hard to understand. Your observations don't always have an obvious conclusion to be drawn. By the way, your book, for some reason, describes your brain as being 500 million interconnected neurons. There are organisms that have that many. We have many more. We have almost 100 billion neurons. I'm not sure why your book uses that figure. It's not important for us today, but we'll talk about the brain in a later unit coming soon. So just one little comment there. Also, we have variability when it comes to psychology, at least. Microorganisms can be very similar within the same species. Stars within the same type of star can be very similar. But human beings have a lot of variability. And of course, that could be partially our egotism when it comes to our own species. That if you ask a star or microorganism, they might think there's just as much variability between members of their group. But for us, we're humans, we care about humans, we're interested in humans, and certainly as psychologists. So the differences between people are important to us. We can't claim that everyone is the same because everyone isn't. Everyone differs along a number of axes, physically, psychologically, um, and behaviorally, certainly. So that variability means we can't just make one or a handful of observations, and we can't just observe one person and hope to say something about people in general. Also, and this is particular to psychology, observing people can change the results, can change what your data say, if the people are aware that you're observing them. This is what's called reactivity. And we'll talk about a specific kind of reactivity here in a minute. But people behave differently when they know they're being watched, when they're being observed. And so just being present as an observer can change the data. So if you're using your senses, and which means you're physically present and not hidden, uh, people can be aware of that, and that can change how they behave. And so that would change our conclusion about human psychology. It would make it untrue, not based on evidence, but based on skewed evidence, evidence that was biased by the fact that people knew they were being observed. So how do we make measurements? If we're going to measure something, and perhaps not rely on our senses, how do we make those measurements? Well, of course, the first thing is we have to ask what we're measuring. And here, an operational definition becomes really useful. And what an operational definition is a way of describing what you're measuring and making sure that what you're measuring is both concrete and measurable. So it's something real, and it's something measurable. It's something tractable for observation, often something tangible. So, for example, if you were interested in studying happiness, uh, and you said, well, we're going to measure it according to how the person feels inside. Well, that's not particularly concrete. So what does that even mean? How they feel? How do we describe a feeling? How do we quantify and really and put a definition on a feeling? It's also not measurable. It's an internal state. So you haven't really defined what you're measuring, and you couldn't measure it even if you did. So how they feel inside is not a very good operational definition for happiness. Your book uses the example of smiling, which is a much better definition. It's concrete. We can define it in terms of a set of facial movements, and it's also measurable. We can witness those movements. We can either through our senses or using a computer and a camera measure smiling. So that's a much better operational definition. Another example, if I was interested in people's math ability, I might say, well, it's the number of steps it takes them in their head to solve the problem. Well, that's fairly concrete, steps, that's quantifiable, but it's not very measurable. We don't know what's going on inside their head. So it fails the second criterion. Whereas the number of problems they get right on a written quiz would be much better operational definition for mathematical ability. It's both concrete and measurable. Definition should also be valid. And so your book uses the term validity. If you want to get technical, this is what's known as construct validity, which is the thing that you're measuring actually has something to do with the phenomenon you're interested in. So if I was interested in happiness, smiling is a pretty valid measurement to make. It's a pretty valid construct. It's not perfect. People smile for reasons other than being happy. They might smile because they're faking it, because they want people to think they're happy. And they might also be happy and not smile. So there's not a perfect relationship between smiling and happiness, but it's pretty good. Whereas crying would be a terribly invalid method for measuring happiness. Some people do cry when they're happy on occasion, but it's not representative of happiness overall. And in fact, people, of course, cry for other reasons as well. So that would have even less validity than smiling. Measurement should be detectable by an instrument. And an instrument is something that's capable of measuring whatever your operational definition describes. So an instrument for measuring smiling could be our senses. It could be a computer with facial recognition that records images of faces and measures if they're smiling or not. That would be a good instrument. but there are all sorts of instruments that pair up with operational definitions. An instrument should be reliable and what we call powerful. So reliable means that if you measure the same thing twice, your instrument should give you the same or close to the same measurement. If it's all over the place, that's not a very reliable instrument. That often involves calibrating the instrument, giving it a known quantity, for example, giving a person who you know is smiling and making sure that it says they're smiling and that it's consistent in terms of how big the smile is, for example, if that's what you're measuring. And then powerful means that it can detect small changes in the quantity. So a good instrument for happiness with this operational definition would be an instrument that can detect small changes in how much the person is smiling. If it can only say smiling or not smiling, that's not all that powerful. But if it can detect those smaller changes, then it becomes more powerful. So another example is the relationship between health and body weight. So body weight is often used as an operational definition for health. And it is concrete, and it is measurable. There are questions about how valid it is. So somebody could be healthy and have an array of body weights, and somebody could be unhealthy and have an array of body weights. So being severely underweight is dangerous, being severely overweight is dangerous. And of course, to be a better measure, be a better construct, a more valid construct, it has to take the person's height into account. So you have things like BMI, the body mass index, which uses two measurements. And of course, the BMI itself is not perfect either, because you can have differences in musculature, for example. Things vary by sex, by age. And so even combining health and weight might not be sufficient to really say something about health. So height plus weight may not be exactly the right construct. And of course, that often will say nothing about the person's disease state. So at best, it gives us a very rough idea. And of course, the measurements, the instruments we're using to measure, have to be good. So how good is the scale we're using? Is it reliable? Does it give us the same readout for the same mass? Is it powerful? Can it detect small changes in weight? Or does it only give us the weight in 50-pound increments, which is not nearly as useful, of course. People don't fall into convenient 50-pound categories. And so the scale, what we're using to measure height, these things are important, and they really inform how good our empirical science will be. So we're going to spend some time here talking about a phenomenon that is really particular to psychology, and that is the effect of expectations. And the most prominent form of this is what are known as demand characteristics. And this is where the fact that the participant in the experiment, knows they're being observed changes what the outcome of the experiment is, changes the data, and specifically changes it such that the participant behaves in a way they think they should, either because they want to be viewed as a good person or because they want to please the experimenter. And so that's what demand characteristics are. And so depending on how big a screen you're doing this video on, there's this cartoon down here in the lower left, and this is a cartoon of Pavlov's dog. And the dog says to his friend, saying, "Watch what I can make Pavlov do. As soon as I drool, he'll smile and write in his little book." So Pavlov, the scientist, thinks he's getting accurate observations about the dog's behavior. But the dog is really just trying to elicit some reaction on the part of Pavlov. And so that's an example of demand characteristics. More commonly, if you're observing people in a social situation and they know you're observing them, they'll act in more socially appropriate ways or act in more socially desirable ways. Or if the person knows what the experiment is about, they may, consciously or otherwise, behave in such a way that they think they will help the experiment turn out the way the experimenter wants it to. So if the experimenter has some hypothesis that can be either said explicitly or inferred from the experiment, the participant may act in a way that confirms the hypothesis artificially. And there are ways to counteract this phenomenon. So one is through what are called naturalistic observations. So this is where you're not running an experiment, where you're just observing people out in public. And you're allowed to do that. So you're watching people behave in their natural environment. They're not aware that you're recording anything, and they're just behaving as they normally would. Now, again, this is the sort of thing that can be done in public where people don't have an expectation of privacy. Naturalistic observations cannot be done ethically in somebody's home, for example. But just being out in public and observing or recording behavior is one way to get around demand characteristics. That way the people don't know they're being observed. Another way to counteract demand characteristics is through privacy and anonymity. So people often behave more naturally or give a more representative example of behavior if they think they're doing so privately, especially for things like surveys. If you leave them alone, they're more likely to answer the survey honestly than if you sit there watching them. Anonymity is also a big one. If people don't know that their behavior can be connected back to their identity, they behave in more honest ways. Again, especially when it comes to things like what are socially appropriate behaviors. Do people really adhere to social norms of honesty, of generosity? And if they are perfectly free to behave selfishly but be anonymous about it, they're much more likely to do it. And so the question is, how do you get the most accurate representation of behavior? And one of the ways is to remove the effect of yourself as the experimenter and observer. You can also make it clear the person's in an experiment, but you can disguise the purpose of the experiment or the purpose of the observation. So if you have someone engage in an economic task where they have to trust someone, if you say the experiment's about trust, they're going to behave very differently than if you say the experiment is about financial management. And so saying what the experiment is about can alter what the person does. Again, in an effort to adhere to social norms or to try to behave well or get the best performance in the domain in which the experiment is described, which is why in many experiments there's some degree of deception or at least withholding of what the point of the experiment is. That's told afterwards. We'll get to that later. But it is acceptable ethically in most cases not to reveal what the point of the experiment is until afterwards. That way, the person doesn't keep the point of the experiment in mind and behave accordingly. Of course, expectations don't just come from the participant. They can also come from the experimenter. So you have phenomena such as observer bias. So the observer, the experimenter, knows what the experiment's about, knows about whether the person is in an experimental or a control group. We'll get to that definition later. Knows what the person might do if the hypothesis is true, if the theory is accurate. And so observer bias is, which is what it sounds like, it's bias on the part of the observer, where data might be interpreted in a certain way, observations might be categorized one way if it confirms the hypothesis and another way if it doesn't. Data might be kept or thrown out based on what the observer expects to happen. And this can be done consciously or it can be done sort of unconsciously. I mean, you're never going to unconsciously throw away data, but you might rationalize it. You might say, oh, well, this participant was clearly odd in some way. I should not count their data because they're not representative. And this sort of thing can happen from time to time, which is why you have to be very careful as an experimenter not to let your hypothesis dictate what you do with your data. Also, if you're directly observing a participant, you can often give off subtle cues. So you might smile when the person does something that confirms your hypothesis, or you might nod, or you might encourage them in some way. And then again, this could be totally unconscious. So one of the ways to counteract this is through double-blind studies. So that is, neither the participant nor the experimenter knows whether the participant is in the control or experimental group. So that way, the observer doesn't even know what behavior by the participant would confirm or disprove the hypothesis. So they can't affect behavior, at least not in a systematic way that would alter the results. Okay, so we've had some sort of empirical endeavor, an experiment maybe. We've taken our observations, our measurements. Now what do we do with it? So how do we describe what we measure? And the thing is that experiments, even simple behavioral experiments where the person smiles or doesn't, or they make a certain decision, they count a certain number of dots in a certain amount of time, really simple stuff. With repeated observations and a large number of participants, experiments can generate a lot of data. And so the question is, how do we summarize those data? How do we convey what the results are, especially to a naive audience? We might know what the data are, so maybe we don't need as much summarization. But a colleague might need a little more, might need you to digest the results for them a little bit. And the public, of course, needs even more summary, or needs even multiple ways of conveying results. So one way to reveal results, to present them, is graphically. So you just give them a picture. A picture is worth 1,000 words. And one of those common ways, if you are measuring one thing, is to give what's called a frequency distribution. And this is often in the form of what we call a histogram, which in this case is a curve, but could also be a bar graph, just indicating how many measurements we had of a given value. So in this diagram, we see men and women split into two groups. And we can see that the curve for women is slightly to the right of the curve for men. But each curve, for any given value on the x-axis, which is our observation value, in this case it's the score on a motor skill test, can be paired with its height. So the y-axis is the number of people with that particular measurement. So just from this picture, we can see what the most common measurement was for men and women, where the middle of the measurements was, how wide, how variable, and we'll get into this here more in a minute, how variable the observations are. But this gives us a graphical representation of all of our observations. It's way easier to interpret visually this way than to give someone a page full of numbers. And especially with really large data sets in modern science, you can have data that totals gigabytes. And not only is that not something you can wrap your head around, it's not even something you can publish. And so you have to summarize the data in ways like this, via graphs. Now, these data adhere to what we call a normal distribution, which is sometimes called a Gaussian distribution or even just a bell curve. You can see it's sort of bell-shaped. So these data are Gaussian or normally distributed. Not all data are. A lot of physiological measurements are. Things like height will adhere to a Gaussian distribution. Weight will adhere to a Gaussian distribution. But not all measurements do. So for example, this is a graph, a histogram, so the same sort of representation. But here we're looking at household income in the United States. And this does not adhere to a Gaussian distribution. So it's not this bell curve with data evenly distributed around a middle. So here we can see it's not that way at all. That the vast majority of observations are on the lower end of our income measurement, with only a few on the upper end, and then a small handful in the extreme upper end that have to be clumped together because they're so large they'd run off the end of the graph. So again, most, at least perhaps data in psychophysiology or psychology, will give you one of these bell curves, but not all data do. So we have to be careful about that, not to assume one of these normal distributions. But you don't always have to use a graphical display of your data. You can use descriptive statistics, which are numerical summaries of your data. So using just a couple of numbers, you can give the listener a pretty good idea of the observations that you made. One way of describing data is through what is called the central tendency. which is just a way of saying where's the middle of the distribution of your data. Another way is describing the variability, and usually you will give both. One isn't particularly useful without the other. And variability is how similar everyone is to one another, and therefore to the middle. So if you have zero variability, that means every observation that you made gave the same value. So in our previous example, if everyone had the same income, the central tendency would be that value, that income, and the variability would be zero. There's no variability. Everyone is exactly the same. And that almost never happens in real-world observations. So we give a number to describe how variable the population is, or the sample is. And there are a couple different ways of describing the central tendency. One is through the mode, which is the most frequent value. So in this new picture here on the right, you can see all the observations that were made. In this case, the observations are test scores. And again, the y-axis is how many observations of a given value were made. So the left picture, we have this nice curve. In the right picture, we have individual observations. But in both cases, we can say what the mode is. We can look at the curve or the data on the right and figure out what is the most common measurement. For happiness study on the left, is the peak of that curve. Whatever measurement that lines up with, that is the mode. In the picture on the right, the mode is 3. So if you look at the observations, the value 3 has more observations than any other, so it's the mode. You can, of course, also give the mean, which is the average value. Now, on the picture on the left, if that distribution is totally symmetrical, then that average value will still be the peak. The mode and the mean will be the same thing. On the right, we can actually calculate the mean. So here we add up the values of all the observations, divide by the number of observations. That gives us a mean or an average. And that's a really common thing to do, not just in statistics, but in life in general, figuring out what your average household expenditure is, for example. And so the mean is probably the most frequently used measure of central tendency, but it's not always the most representative one. Not always the right one to use. Because if the data aren't symmetrically distributed, the average can be really misleading. Then you have the median, which is if you put all the values in order, it's the one in the middle. So it can be a little biased by extreme values, but not nearly as much as the mean is. The mode isn't biased by extreme values at all. It just picks the most frequent one. So the median is also a common way of describing where that middle is, where that central tendency is. In this case, the median is also 3 on the right, because again, if you order all the values, that middle value is 3. And these metrics, as I've already alluded to, can differ. It depends on the shape of that distribution, the shape of that curve. So in this example, we have a perfectly symmetrical Gaussian or normal distribution. The mean, the median, and the mode are all the same thing. So that middle value, that central tendency, is the same no matter how you describe it, which of those 3 ways you pick. So the most common value is the peak, because it's symmetrical. The mean value is the peak, and because if you ordered all the values, the peak would be the one in the middle. The median value is the peak. But if the distribution is what we call skewed, then those values start to differ, the mean, median, and mode. Again, the mean can be really biased, can be pulled away by extreme values on one end or the other. So we can see here in the bottom left a distribution where there's this big fat, what we call tail, over on the right. And what that means is most of your observations are toward the left, on the low end. But you have quite a few that are much higher than that. And you even have a few on the far end of the distribution, really huge values. Not many of them, but you do have them. In the middle here at the bottom, we have the opposite case. So we have the peak, which will line up with which will be the mode, and then the mean is pulled toward the left because you have these extreme low values. Not too many of them again, but they are there and they do pull the mean away. So it does matter what way of measuring the central tendency you use. And the differences between those different descriptors will vary with the skew of the distribution. That is how lopsided it is, how asymmetrical it is. Variability, there aren't as many options. And you can talk about the range, which is the biggest value minus the smallest. That's pretty straightforward. You take the maximum minus the minimum, and that's the range. And that's a fairly intuitive measure of variability. But of course, it doesn't account for how rare those extreme values are. If 99% of people are right at the middle, and then you have one really high individual and a really low individual, the range will be the same as if that distribution were a little more spread out, more smooth. And so the range is a good start, but not the most common way of describing variability. The most common way is through the standard deviation, which is denoted by the small Greek letter sigma. And so you'll hear people talk about the standard deviation, and that is a statistical formula. It's a number given to you by this formula that describes variability. And we don't need to go into math here, but we were talking about Gaussian and normal distributions. This is the equation for a Gaussian distribution, and we don't need to go into detail, but for example, that Gaussian distribution is defined by only two quantities, and it's the two that we've been talking about. So I've just circled in blue mu, which is the mean, the central tendency. So the mean of a Gaussian distribution is just part of its formula. So you can define a Gaussian distribution according to the mean, where the middle is. And then sigma, we can see in two places here, but still, it informs the shape of the distribution. So a standard Gaussian distribution, like the ones we're seeing in the middle on the left and above this equation, those are defined by really two numbers, where the middle is and how wide the distribution is, how far people tend to deviate from the middle. Okay, so we have our data, and we can use descriptive statistics. So what do the data look like? What does that distribution look like? We can also analyze the data in a little more sophisticated way. It's going to take a little more work than the mode or the mean or the standard deviation. But it's going to be more informative. And that is through correlation. So as you can see, the word correlation itself, correlation. So it's how two variables or two events relate to one another. So it's a relationship between two sets of numbers. And those numbers are what we could call variables, just like you did in algebra. That is something that can take on multiple values. It's variable. So for example, you can have a positive correlation. That's when one number increases as the other one increases. So there are lots of examples of positive correlations. Hopefully, one of them is in this class. The more you study, the better you'll do. Your book uses the example of a memory test, where the more sleep you get the night before, the more presidents you can recall on a test the next day. So those are positive correlations. The more of one thing happens, the more the other happens. You can have the opposite. You can have a negative correlation. So as one quantity goes up, the other quantity goes down. And your book has another good example here. So cigarettes smoked and years lived, or longevity. So the more cigarettes you smoke, the fewer years you tend to live. So as one number goes up, the other number goes down. That's a negative correlation. And this can be summarized in a single number. And this number is referred to as the correlation coefficient, otherwise known as R. So just like we had a central tendency, it was a single number, we can have a correlation coefficient that's a single number that describes how one variable relates to another. And in this case, the way R is defined, R always varies between -1 and 1. Those are the minimum and maximum values it can take on. So if R is -1, that means a really strong negative correlation. If R is +1, it means a really strong positive correlation. So some examples. This is a really strong, in fact it's perfect, positive correlation. So here what we have is one variable plotted on the x-axis, the other variable plotted on the y-axis, and we can see how they vary with one another. So in this case, if one variable goes up, the other variable goes up too. And it goes up by a consistent amount. So if you go up 5 units on variable 1, you'll go up proportionally 5 units on variable 2. Now the scales can differ. We don't need to get into details there. But the point is that you can, with an R of 1, perfectly predict one variable if you're given the value of the other. You can have an R of -1, a perfect negative correlation. And again, if it's perfect like this, you can take one variable and predict what the other variable will be because you have a perfect relationship. It's totally predictable. Data aren't usually like that. In fact, you may get no correlation whatsoever. There may be no relationship between the variables you're looking at, in which case you'll get a graph like this one on the right. So here the dots are all over the place. There's no consistent relationship between variable 1 and variable 2. So the idea here is that the more extreme values of R indicate a more consistent relationship. So extreme could be negative or positive. It just depends on the nature of the relationship between the variables. So again, if you have an R of 0, no correlation. It's just sort of a cloud of points if you graph the data. There's no relationship discernible. An R of 0.5 would be a positive correlation, but it's not perfect. So there's still some variability there. There's still something you haven't explained. You can't perfectly predict variable 2 given variable 1. You can give a range, you can give an estimate, but it's not a perfect relationship. So they have some relation between the two variables, but it's not totally predictable. An R of 0.9, it's not quite 1, but it's close. So there you can give a really much tighter estimate of what variable 2 will be if you're given the value of variable 1. So the negative or positive sign matters, and also how extreme the value is matters. So the more extreme the value, the more consistent the relationship, the better you can predict one variable from the other. Okay, so correlations are interesting, but we have to be careful with them. So we've got two variables that are correlated, and I think your book uses a good example. You've got watching violent television or movies, so watching violent entertainment, and actual aggression in children. And so the question first is, are they related? Is there a relationship between the two such that you might predict one from the other? Let's say there turns out to be. So there is a correlation. It doesn't mean that one necessarily causes the other. And this is the origin of the phrase, correlation does not imply causation. So for example, X could cause Y. That is, watching violent movies and television might inspire children to exhibit aggressive or violent behaviors. Not an unreasonable hypothesis, but it's not for certain with just the data that we have so far. Because also, Y could cause X. It could be that children that are already more aggressive or violent are drawn to watching aggressive or violent movies and television. So that relationship could go either way. We can't jump to the conclusion that watching violent TV makes a person aggressive or violent. And of course, neither of those could be true. It could be that some third variable, Z, causes both. And this is what's called a third variable correlation. So in your book, the example is lack of adult supervision. Maybe if no one is watching a child, that child tends to become more aggressive, and that child tends to watch whatever they want to watch, which could be violent movies and television. That's just one possible third variable, though. There could be other predictors. Maybe there is a genetic predisposition toward both of those behaviors. it's impossible to tell. So how do you deal with that just from those data? Well, you can't with just those data, but you can apply an additional technique to alleviate that third variable problem. One way of doing it is what's called the matched samples technique. And that's where whatever the variable z is, in this case parental supervision, everyone is the same. You only recruit participants that have the same level of adult supervision. So that way, if you see that correlation, it can't be due to some variation in adult supervision because there is none. You've eliminated the variability in adult supervision. So differences between children that watch violent programs and children that don't can't be because of adult supervision. Another way of addressing it, and this is a little bit easier, trying to find a whole bunch of people with exactly the same value for a given variable can be tough. Another way is with the matched pairs technique. And that way, each participant, it's not that all the participants have the same value for variable z, but for each participant, there's someone in each group, whether you're exposed to violent programs or not, that has the same level of adult supervision. So it's not that everyone has the exact same value of z, but for every person that watches violent TV, there is a counterpart that doesn't, that has the same level of adult supervision. So this way, the average amount of supervision works out to be the same between the two groups. And that's another way of going about it. So either way, whatever correlation you see, if there still is one, can't be due to variable z because there is no variable z. There's no variation in it. And so if there's still a relationship, it can't be due to parental supervision. You've eliminated that possibility by making sure everyone's the same on both ends of the spectrum for that variable. But it could be due to some other variable. I already mentioned genetics. It could be due to peer influence. Maybe the aggressive individuals have aggressive peers and the non-aggressive individuals have non-aggressive peers. You didn't measure that, so you don't know. And the real trouble is there's an infinite number of third variables. So you can't solve the problem for all third variables. You can only solve it for particular third variables using just simple correlational approaches like this one. Now, the way to get around that is with an actual experiment. Here, you're not just observing variable 1 and variable 2 and seeing if there's a relationship. You're going to have an experiment that can really establish a causal relationship between those two variables. So you're going to set up the way you've made your observations to where you can make that determination of causality. And this is done by what's called a manipulation. So you're going to change the environment, or you're going to change something about the individual for what's called the independent variable. And the independent variable is the thing you're manipulating. It's something about the person or their circumstances that you're going to intentionally alter. And what this does is it splits your participants into experimental and control groups. Now, you probably already heard the term control group, and the experimental group is the group you manipulated. The control group you leave alone. So the experimental group has that independent variable manipulated, and the control group doesn't. So in our previous example, the control group is not exposed to violent programs, movies, and TV. The experimental group is. So you've changed something about that group, and now you're going to see what happens. Now, the thing is, the really important part of doing an experiment like this, these two groups, is that you have to randomly assign the groups. And this is really, really important because if you have enough people, if you randomly assign the groups, if you flip a coin to determine whether someone's in the experimental or control group, all of those possible third variables should wash away. If you've got 100 people and you split them into two groups of 50 and they're randomly split, then of those 50, of those two groups of 50, you should have the same average levels of parental supervision, of genetics, of income, if you're just randomly selecting people. And again, it depends on the size of the groups you're dealing with. If you just picked one person and put them in each group, they're going to vary on all sorts of ways. But with big enough groups, you can sort of average out all the differences that might occur between two individuals. And so the random assignment is really important. You don't want to do what's called self-selection, where you offer them the choice of watching violent programs or not, because then they're not going to be randomly assigned. And people that choose to watch violent programs may be different in a lot of ways from people that choose not to. So if you don't randomly assign them, if they self-select or you select them, you could be reintroducing those third variables, and you don't want to do that. So you need to randomly assign the experimental and control groups. And then what you do is you measure the value of the dependent variable between those two groups. So in this case, it's aggressive behavior. That's the dependent variable. You're seeing if you manipulate the independent one, exposure to violent programs, that it even has an effect on the dependent one, aggressive behavior. And now you can really say whether exposure to violent media causes changes in aggressive behavior. Well, whereas before, it was just a correlation. And so there could be any number of causes. Here, you've kept everything the same between the two groups, except for your one variable, your manipulation, their exposure to violent programs. And by randomly assigning the groups, you've, again, sort of averaged away other sources of variation, other causes for the dependent variable. Okay, so that will do it for this lecture. Next time, we're going to continue our discussion of the science of psychology, and we're going to ask, what do we do once we're done measuring? So we've already started that. We've talked about correlations. We started talking about experiments. And then we're going to follow this up next time with how we draw conclusions from our data once we've collected it, to make sure that we don't draw wrong conclusions or conclusions that aren't warranted by what the data say. We're also going to talk about avoiding the effects of expectation. So sometimes we expect data to come out a certain way, or we expect our hypothesis to be confirmed, and we need to let that not bias what conclusion we actually reach. And finally, we're going to talk about ethics. And ethics is a very important topic in science. It hasn't always been as important as it needs to be. But now, especially psychologists, are very aware of ethics. And ethics covers a range of topics, most notably how we treat participants. So we're dealing with human beings for the most part, also with animals sometimes. But mostly with human beings, we have to be very respectful of those human beings. And so we'll cover all of that next time, and I will see you then.